Chapter 15 is mainly a continuation of Chapter 14, where we consider the strength of a linear relationship between two variables. In this chapter, we will focus on the idea of prediction. For instance, if we can establish that two variables have a strong association, can we somehow quantify the changes in the response variable with the value of the explanatory variable? Can we use the value of the explanatory variable to predict the value of the response variable? These are the concepts that we will discuss in Chapter 15. Regression lines, regression equations, understanding prediction, correlation in regression, the question of causation, and evidence of causation. If a scatter plot shows a straight line relationship between two quantitative variables, we can summarize the overall pattern by drawing a line on the graph. A regression line summarizes the relationship between two variables, but only in one specific setting, one where one of the variables helps explain or predict the other. In general, a regression line is a straight line that helps describe how a response variable y changes as an explanatory variable x changes. We often use a regression line to predict the value of y for a given value of x. For example, let's recall the example where we computed the correlation between femur length and humerus length. The correlation was very close to +1, indicating a very strong linear relationship. The regression line would be a single line that represents the general relationship between these two variables. For example, we'd expect to see something like this. Because the correlation is so close to +1, our data points are very close to the regression line. When a plot shows a straight line relationship, it is easy to draw a line close to the points by eye. However, without a definite process for finding the line, different people might draw different lines. Because we want to predict y from x, we want the line to be as close to the points in the vertical direction as possible. We need a way to find from the data the equation of the line that comes closest to the points in this vertical direction. The most commonly used regression line for this purpose is the least squares regression line. The least squares regression line of y on x is the line that makes the sum of the squares of the vertical distances of the data points to the line as small as possible. If you recall, we typically use x to stand for the explanatory variable and y for the response variable. With this in mind, the equation of the regression line can be written in the form y equals a plus bx. The number b is the slope of the line, the amount by which y changes when x increases by 1 unit. The number a is the intercept, or the y-intercept, the value of y when x equals 0. To use the equation for prediction, just substitute your x value into the equation and calculate the resulting y value. For instance, let's return to the example relating femur length and humerus length. The regression line was chosen by choosing the one that makes the vertical distance between the line and the points as small as possible. So if x denotes our femur length and y denotes our humerus length, then it turns out that the least squares regression line is y equals negative 3.66 plus 1.197x. The slope of this line is 1.197. This means that for these fossils, humerus length goes up by 1.197 centimeters when the femur length goes up by 1 centimeter. The intercept of the least squares regression line is negative 3.66. This is the value of the predicted y when x is equal to 0. Now you try one. Use the equation of the least squares regression line from the previous example to predict the humerus length for a fossil with a femur length of 70 centimeters. So pause the video and unpause when you're ready for the answer. To use the least squares regression line to predict the humerus length, we will substitute the given value of the femur length. So we would get negative 3.66 plus 1.197 times 70, which simplifies the negative 3.66 plus 83.79, which gives us a predicted humerus length of 80.13 centimeters. In practice, we often use several explanatory variables to predict a response variable. Although the details are messy, all statistical methods of predicting a response share some of the basic properties of the least squares regression line. In general, prediction is based on fitting some model to a set of data. Prediction works best when the model fits the data closely. Also, beware of extrapolation. This occurs when we try to use our model to predict a value that is wildly outside the range of the available data. So let's begin discussing the relationship between correlation and regression. If you recall, correlation measures the direction and strength of a straight line relationship. Regression then comes in and draws a line to describe this relationship. Now, correlation and regression are closely connected, even though regression requires choosing an explanatory variable and correlation does not. However, both correlation and regression are strongly affected by outliers. For instance, consider the scatter plot to the right. The solid line is the regression line found using all 50 observations. The dotted line is the regression line found when omitting the outlier around 15,350. Notice how different the resulting regression lines would be. The usefulness of the regression line for prediction depends on the strength of the association. It turns out that the square of the correlation is the right thing to look at when determining this usefulness. In general, the square of the correlation r squared is the proportion of the variation in the values of y that is explained by the least squares regression of y on x. The idea is that when there is a straight line relationship, some of the variation in y is accounted for by the fact that as x changes, it pulls y along with it. In reporting a regression, it is usual to give r squared as a measure of how successful the regression was in explaining the response. When you see a correlation, square it to get a better feel for the strength of the association. For instance, if we have perfect correlation, meaning that r is equal to -1 or +1, this means that the points lie exactly on a line. In this case, r squared would be equal to 1, and 100% of the variation in one variable is accounted for by the straight line relationship with the other. If, for instance, r equals negative 0.7 or 0.7, then r squared is equal to 0.49. So in this case, about 50% of the variation is accounted for by the straight line relationship. The other 50% of the variation is due to other factors. However, we must keep in mind when using prediction models that association and causation are not the same thing. In general, here are some things to keep in mind when trying to understand the influence one variable has on another. First, a strong relationship between two variables does not always mean that changes in one variable causes changes in the other. The relationship between two variables is often influenced by other variables lurking in the background. The best evidence for causation comes from randomized comparative experiments. For instance, when trying to establish a cause and effect relationship, we must be mindful of the effect of lurking variables. Let's look at an example that highlights this. Here we will investigate the relationship between television sets per person and life expectancy for each nation. In this case, there is a strong positive correlation. So does this mean we could lengthen the lives of people by giving them more television sets? In this case, both our explanatory and response variables are responding to some lurking variable. Rich nations do have more TV sets. However, rich nations also have better access to nutrition, clean water, and health care. In general, we would call a situation like this common response. This is a situation where both the explanatory and response variable are responding to some lurking variable. In addition, even if there is a cause and effect relationship that is present, it is often not a complete description of the association. So let's look at another example. Researchers measured the BMI of several Mexican American girls aged 9 to 12. They were interested in investigating the relationship between BMI and lifestyle choices. They found that the girls' BMIs were weakly correlated with physical activity, diet, and television usage. The strongest correlation they observed was between the girls' BMI and their mother's BMI. In general, remember to consider whether two variables are confounded when trying to establish a cause and effect relationship. In summary, the observed relationship between two variables may be due to direct causation, common response, or confounding. Two or more of these factors may be present together. An observed relationship can, however, be used for prediction without worrying about causation, as long as the patterns found in past data continue to hold true. Now, despite all these difficulties, it is sometimes possible to build a strong case for causation in the absence of experiments. So what are the criteria for establishing causation? First, the association must be strong. The association needs to be consistent. Higher doses need to be associated with stronger responses. The alleged cause precedes the effect in time, and the alleged cause is plausible.